Assalamualaikum and hello everyone, my name is SYAHIRA binti Muhammad Zaki. Today I'll be presenting introduction and application of heat implant. Basically, this slide explains the application of heat implant or prosthesis. The heat implant are mainly used to improve mobility and function by restoring a patient's ability to walk, stand and perform daily activities, which increases patient's independence. They are also commonly used to manage hip fractures, especially in elderly patients when the bone cannot heal properly. This allows early mobilization and faster recovery. In addition, heat implants are used to treat hip joint diseases such as osteoarthritis, rheumatoid arthritis, and vascular necrosis, helping to reduce pain and improve joint movement. Lastly, heat implant can correct hip deformities, whether congenital or acquired, by restoring proper joint alignment and normal biomechanics. Overall, they provide a long-term solution using biocompatible materials. This slide shows the main component of a heat implant. First, the acetabular cup is an artificial socket placed in the pelvis, which replaces the natural hip socket. Inside the cup is the liner, also called the insert, which provides smooth, low-friction movement during joint motion. Next, the femoral head or ball replaces the natural femoral head and articulates with the liner to allow movement. Finally, the femoral stem is inserted into the femur and supports the femoral head, providing stability to the implant. This slide shows the general material commonly used in hip implants, which can be divided into metal, ceramic, polymers, and material combinations. First, metals such as titanium and titanium alloys are widely used because of their high biocompatibility, lightweight, and corrosion resistant. They are commonly used for the femoral stem. Cobalt chromium alloys are much stronger and wear resistant, making them suitable for high load bearing parts like the femoral head and acetabular cup. Next, ceramic like alumina and zirconia have extremely smooth surfaces and very low wear rates. They reduce friction and particle generation and are often used for femoral heads and liner. Polymers, especially ultra-high molecular weight polyethylene, act as liners between metal or ceramic surfaces. They provide low friction, good wear resistance, and absorb shock during movement. Lastly, common material combinations such as ceramic on polyethylene, metal on polyethylene, and ceramic on ceramic are chosen to balance durability, wear resistance, and patient safety. Hip joint damage causes pain where it reduces patient's mobility and leads to poor quality of life. In advanced conditions, current treatment solutions are limited and often ineffective. Therefore, an improved hip implant design is required to ensure better durability and functionality. The objective of this design are to restore hip movement and joint function and to reduce pain and discomfort. In addition, the implant is designed to improve biocompatibility and durability while minimizing wear and implant failure.
Assalamualaikum and hi everyone, I am NURADRIANA SYAFIQAH and I'll be presenting our design concept for the novel hip implant. Our design uses a patient-specific femoral stem and acetabular cup created from CT or MRI scan to match the patient's natural hip anatomy. This ensures better fit, initial stability and reduced micromotion at the bone implant interface. We chose titanium alloy for its high strength, corrosion resistant and proven biocompatibility, which is ideal for long-term load-bearing application. The implant has a solid internal core for mechanical strength, surrounded by a gradient porous structure that allows bone ingrowth for stable long-term fixation. The joint surface is made of a ceramic femoral head paired with a highly cross-linked polyethylene liner, which reduces wear and friction, minimizing inflammatory responses. Finally, a modular neck design allows surgeons to adjust leg length and hip offset during surgery, improving joint alignment and post-operative mobility. Now, let's look at why this design was chosen. First, it enables physiological load transfer as the porous structure lowers implant stiffness to more closely match natural bone. This reduces stress shielding and helps preserve surrounding bone. By reducing stress shielding, we prevent bone resorption and enhance implant stability over the long term. The precise anatomical fit and porous surface improve implant stability by reducing micromotion at the bone implant interface, lowering the risk of loosening. Because it is adaptable to different patients, it suits varying bone qualities and anatomies, from elderly patients with weaker bone to active younger patients. Finally, this customization restores hip joint biomechanics, improving comfort, mobility, and post-operative function. Our design has several advantages over conventional hip implants. The porous surface allows bone to go directly into the implant, providing strong biological fixation without heavy reliance on bone cement. The ceramic on polyethylene bearing generate fewer wear particles, reducing the risk of osteolysis and inflammation, which are common cause of implant failure. Because of this feature, the implant shows lower revision rate, reducing the need for secondary surgeries. The modular neck design also improves joint biomechanics, resulting in smoother gait and better mobility. Overall, patient experience reduced pain, faster recovery, and improved functional outcomes, which increases satisfaction after surgery. Finally, our design improves performance and longevity. The solid core and porous structure provide long-term mechanical stability and support repeated loading over many years. Low wear rate of the ceramic on polyethylene interface extended implant functional lifespan, which is expected to exceed 15 to 20 years. By promoting bone ingrowth, the risk of implant loosening is reduced, which also lowers the likelihood of revision surgery. This improvement contributes to cost effectiveness over time, as fewer complications and longer-lasting performance reduce long-term healthcare costs, despite a slightly higher initial implant price. In summary, our patient-specific gradient porous hip implant combines biomechanical efficiency, advanced materials, and customized alignment to improve implant performance, longevity, and patient outcomes.
Assalamualaikum and hi, my name is DAYANG FARZANA and I will briefly introduce the overall design and main components of our proposed hip implant. The implant consists of 5 key parts: the femoral stem, modular neck, femoral head, polyethylene liner, and acetabular cup. The femoral stem is the main load-bearing component inserted into the femur. It is made from titanium 6 aluminum 4 vanadium titanium alloy and features a solid core with a gradient porous outer surface. Attached to the stem is the modular neck, which is also made from the same titanium alloy. This connects the stem to the femoral head. The femoral head is manufactured from medical-grade ceramic, forming the articulating surface of the hip joint. This ceramic head articulates with a polyethylene liner, typically made from ultra-high molecular weight polyethylene or UHMWPE. Finally, the liner is housed within the acetabular cup, which is also made from titanium alloy and is fixed into the pelvic bone. Together, these components form a complete hip implant system designed for strength, durability, and smooth joint movement. I will now explain the fabrication processes used to produce this hip implant. The process begins with patient data acquisition, where CT or MRI scans of the patient's hip are obtained and converted into 3D digital models. Next, computer-aided design, or CAD, is used to design the customized femoral stem and acetabular cup. This includes defining the solid internal core, gradient porous outer structure, and modular neck interface. The titanium components are then fabricated using metal additive manufacturing, specifically using titanium 6 aluminum 4 vanadium titanium alloy powder. This method allows the creation of complex geometries, including controlled porous structures and dense load-bearing regions within a single component. After additive manufacturing, the components undergo stress relief heat treatment to reduce residual stresses and improve mechanical reliability. This is followed by precision machining and finishing, where critical interfaces such as taper junctions and contact surfaces are CNC machined to achieve accurate dimensions. Non-porous regions are polished, while porous surfaces are left untreated. The modular neck is fabricated separately through precision machining or forging to produce different neck lengths and angles. The ceramic femoral head is manufactured through powder compaction, high-temperature sintering, and polishing, while the polyethylene liner is produced using compression molding and machining. Finally, all components are assembled, cleaned, sterilized, and subjected to quality control and final inspections before use. Overall, the fabrication methods used are closely matched to the properties of each material, and in the next section, ANDRYANA will explain how material suitability contributes to the implant's performance and reliability.
So, I will be explaining the material used in hip implants, focusing on the main components and why specific materials are chosen. A hip implant is made up of 3 main parts: the femoral stem, the femoral head, and the acetabular cup with liner. Each of these components has a different function, so material used must match their role inside the body. When selecting materials for hip implants, there are 4 important factors to consider. First is biocompatibility, which means the material must be safe and not cause harmful reaction in the human body. Second is mechanical properties, such as strength and stiffness, because the hip joint supports body weight and movement. Third is wear resistant, especially at the joint surface where movement happens repeatedly. Lastly, cost and availability are also important, so the implant can be widely used in the hospitals. In the next slides, I will explain the material selection for each hip implant component and the reasons behind these choices. Let's talk about femoral stem. The femoral stem is the part that is inserted into the thigh bone, also known as the femur. Its main function is to support the body's weight and transfer loads from the hip joint to the bone. The most commonly used material for the femoral stem is titanium alloy. This material is chosen mainly because of its excellent biocompatibility and corrosion resistance, which makes it very safe for long-term implantation. Another important reason is its elastic modulus, which is closer to that of natural bone compared to other metals. This helps reduce a problem called stress shielding, where the bone becomes weaker because it carries less load. In addition, titanium alloy has high strength and good fatigue resistance, meaning it can withstand repeated loading during walking or running. Because of these advantages, titanium alloy are widely used in commercial hip implants. Now, let's talk about the femoral head. The femoral head is the bowl-shaped component that fits into the acetabular cup. This part experiences high contact stress and constant movement, so wear resistance is extremely important. The most common material used for the femoral head is cobalt chromium alloy. This material has high hardness and strength, making it suitable for load-bearing application. It also has excellent wear resistance, which helps reduce surface damage during joint movement. Cobalt chromium alloy has proven long-term biocompatibility, meaning it performs well inside the body over many years. However, one disadvantage is that it is more expensive compared to some other materials. An alternative material for the femoral head is ceramic. Ceramic has produced lower wear rates, which help reduce wear debris. However, ceramics are more costly and can be more brittle, so they are usually chosen based on the patient needs and cost consideration. The acetabula cup is the socket part of the hip joint, and it works together with the liner to allow smooth movement. The cup or shell is usually made from titanium alloy. Titanium is chosen because it allows good bone fixation, helping the implant stay stable over time. It also provides strong structural support while remaining biocompatible. The liner, on the other hand, is typically made from ultra-high molecular weight polyethylene. This material is used because it provides low friction, allowing smooth movement between the femoral head and the cup. Polyethylene also acts as a shock absorber, reducing impact forces during walking or running. Compared to conventional plastics, it produces less wear debris, which lowers the risk of inflammation and implant failure. Overall, the combination of a titanium cup and ultra-high molecular weight polyethylene liner is cost-effective, reliable, and widely used in modern hip implants.
Hi, my name is NURUL. I will explain the degradation mechanism in hip implants, the body's response, and how material selection help reduce these effects. First is corrosion. Metallic components in hip implants are constantly exposed to body fluids, so over time this interaction can cause greater surface changes and the release of metal ions. The body may respond with inflammation, which can affect the surrounding tissues. The second mechanism is wear debris. During daily activities like walking, where repetitive motion occurs at the hip joint surfaces, this motion generates microscopic wear particles that can accumulate in surrounding tissues. The body may react to these particles, leading to osteolosis and bone loss. The third mechanism is oxidation, which mainly affects the polymer components such as the UHMWPE liner. In long-term exposure to oxygen and body fluids, it causes gradual degradation of the material, reducing its mechanical performance. This increases the risk of implant loosening. So to minimize these effects, appropriate material selection is crucial. Titanium alloys are commonly used because they have excellent corrosion resistance and highly biocompatible, it reducing the inflammatory reactions. Next, ceramic or cobalt chromium femoral head. It is very hard and wear resistant, producing fewer wear particles and lowering the risk of bone loss. Finally, UHMWPE liner, it has low friction and good durability, which could help in reducing the debris generation and lower the risk of implant loosening.
My name is NABILA EIZATIRODIAH PUTRI BINTI MUHAMAD, matrix number 2468744, and today I'm going to be presenting about device characterization of hip implants. The purpose of device characterization is to ensure safety, performance, and longevity of hip implants. It is to evaluate structure, material composition, mechanical strength, and surface properties. These tests help us to predict wear, corrosion, and biological response in the human body. Firstly, for imaging and surface characterization, scanning electron microscopy, or SEM, is used to observe the implant surface at very high magnification. SEM allows us to examine surface roughness, wear tracks, microcracks, and corrosion pits on components such as the femoral head and acetabular cup. Compared to optical microscopes, SEM provides much higher resolution, making it more suitable for detecting microscopic wear debris that can lead to inflammation or bone loss. Therefore, SEM is the most appropriate tool for analyzing surface damage and wear mechanisms in hip implants. Next, for mechanical characterization, the Instron Universal Testing Machine is used to measure the mechanical strength of hip implant components, to perform tensile, compression, and fatigue tests to simulate the forces experienced during walking, standing, and other daily activities. Instron testing ensures that the femoral stem can withstand body weight without fracture or permanent deformation. Compared to simple hardness tests, Instron provides complete mechanical behavior under load, making it essential for load-bearing implant evaluation. Third, for chemical identification, Fourier transform infrared spectroscopy, or FTIR, is used to identify the chemical composition of implant materials, especially polymers. In hip implants, FTIR is mainly applied to UHMWPE liners to detect oxidation and chemical degradation. Oxidation can reduce the mechanical performance of the liner and increase wear debris. FTIR is a non-destructive technique and is more suitable than X-ray diffraction for polymer analysis, making it ideal for monitoring liner stability. Lastly, contact angle measurement is used to evaluate the surface wettability of implant materials. This method involves placing a liquid droplet on the implant surface and measuring the angle formed. A lower contact angle indicates a more hydrophilic surface, which promotes better cell attachment and bone integration. While surface roughness measures physical texture, contact angle directly reflects biological interaction, making it important for assessing biocompatibility. Each characterization instrument provides different but complementary information. SEM focuses on surface imaging, Instron evaluates mechanical strength, FTIR identifies chemical degradation, and contact angle measurement assesses surface interaction with biological tissues. Using only one method is insufficient, so a combination of techniques is required for complete implant evaluation. In conclusion, proper device characterization is essential to ensure the safety and effectiveness of hip implants. By combining imaging, mechanical testing, chemical identification, and surface analysis, we can reduce implant failure, minimize degradation, and improve efficient outcomes. These characterization methods play a crucial role in designing reliable and long-lasting hip prostheses.